Hi, good afternoon. My name is Valentina Arevalo, and I'm a master's student here in the Mechanical and Aerospace Engineering Department under the supervision of Professor Vinod Narayanan. And we work with a team of other engineers, graduate and undergraduate students. And today I'm going to be presenting a microchannel polymer heat exchanger for residential applications. So the microchannel polymer heat exchanger, which I will be referring in the presentation as MPHX for short, it's aiming to compete with current state-of-the-art, which is a fin tube heat exchanger that has a cross-flow configuration. As we can see here, and we all know in a cross-flow configuration, we have one fluid going in a straight way and the other one going around it, like in cross-flow, right? So because of this type of flow configuration, we are expecting to have low effectiveness. Additionally, due to the tubes that are here in the heat exchanger, we will have an additional pressure drop. Also, these type of heat exchangers are commonly made of metals, which make them more expensive, also more prone to fouling and corrosion, and they are also heavier. So the proposal that we have here is the microchannel polymer heat exchanger. So basically, we have a plate, and how the heat exchanger is built is just a stack of many plates. These plates consist of microchannels, which creates passages for the flow. So as I'm showing in this picture, we have the plates stack. And for example, here, the blue arrows indicate the direction of fluid 1, which in this case is water, for example. And the yellow arrows indicate the direction for fluid 2, which in this case is air. As you can see, they are in a counterflow direction, which benefits heat transfer because this is where we can get the highest effectiveness in a heat exchanger. So another of the benefits of this heat exchanger is that we can easily scale it up in two directions. One is in the vertical direction, so along its height, and the other one is in the horizontal direction, so across its depth. So this is beneficial for us so that because it enables us to make the heat exchanger as big as we need it for the application. Another one of the benefits of this heat exchanger is that it has a lower pressure drop because now the headers are not in the weight of the flow, right? And also the headers have this airfoil shape, which is more aerodynamic and help us to have a lower pressure drop. Additionally, since they are made of polymers, they are lighter. They are also less prone to fouling and corrosion. They are less expensive, and they are potentially less noisy. So some of the applications for this heat exchanger, right now in our lab, there are 2 projects ongoing. One of them is sponsored by the California Energy Commission. In this project, we are aiming to apply this heat exchanger in a secondary loop for an HVAC system. So a little bit of the background here. Currently in the US, air conditioning is responsible of 6% of the electricity consumption. And it's also responsible of more than 100 million metric tons of carbon dioxide per year. Additionally, as we all know, refrigerant leakage is a huge issue in this type of systems, right? And since these systems usually employ high global warming potential refrigerants that cause a huge environmental harm. So right now there is a shift towards moving to low and even super low GWP refrigerants. But its issue is that they have some safety concerns because, for example, they are highly flammable. So that will be dangerous to have a heat exchanger inside a building with other people that has a potential it's highly flammable, right? So the idea here is to have that heat exchanger with the low GWP outside of the building, and then we will employ a secondary loop and that's where our MPH checks will take place. So thanks to when we apply this heat exchanger, then we can mitigate some of the safety hazards due to the flammability of the refrigerants, but also since it is high effective, we can minimize some of the inefficiencies that are implied in having a secondary loop. Another of the applications that we are evaluating in our lab or working currently is sponsored by the Department of Energy, and is using these heat exchangers on data centers. So the background here is that up to 40% of the energy used in a data center is used for cooling. And also hundreds of billions of gallons of fresh water are used annually. So here we are proposing, first of all, designing a cold plate that will dissipate the heat from the chips, so the CPU, GPUs, etc. And then from the cold plate, we will dissipate that heat to the heat exchanger, and the heat exchanger will dissipate it to the atmosphere, and the MPHX that I'm talking here right now. With this application, we are aiming to reduce the data center cooling energy to 5%, and also water won't be required in this application. Okay, so I talked about the applications that we can use the heat exchanger on. Now we want to actually manufacture it. So we are focusing on two ways of manufacture the heat exchanger to scale it up. One of them is 3D printing the heat exchanger, and here I have some samples so that maybe that's easier to watch. I will pass it around and you can see it, yes. So the 3D printed version of it is basically a unit that consists of 20 plates stacked together, and on top of it has some slot for the O-ring so that we can stack them vertically and avoid leaks. So we can stack it vertically as big as we want, and also horizontally, as I mentioned before. This type of application is good for quick prototyping, but it's not feasible in the long term. So we are also analyzing the possibility of using injection molding to manufacture these plates. So here, we will have a single half plate. So imagine a sheet of plastic that on top of it will have the fins for the water channels, and on bottom we'll have the fins for the air channels. So we will have this single half plate, and on top just a plain plastic sheet, so that we can create a single plate. Then we will, of course, as I mentioned before, stack all the plates and create the heat exchanger. But here, the first thing we have to focus on is making a single plate, right? So right now, we are looking for two methods for this. The first method is using laser welding. So there's a company we are collaborating with, and we send some samples and pressure test these samples in our lab, which later I will talk a little bit more about it. And also, we are exploring the possibility of using some adhesive to bond the plates together and create the seal plate. So in the path of injection molding, we needed to make sure that, to actually manufacture this with injection molding, of course, we need a mold, right? But because the plates have these tiny channels, we want to make sure that every single cavity of the mold is actually getting filled by the plastic. So we run several injection molding simulations with an injection molding company here in Santa Rosa. And after many iterations, we found a system, which is this one that I'm showing here on the upper right corner, with a sprue and runner correct size that is able to achieve 100% confidence of fill of the plastic, and also the injection pressure values, pressure drop, and filling time, it's it's good and it's as expected in injection molding. So right now we are in the process of manufacturing the mold so that we can manufacture the actual plates out of this. Well, just a little bit talking about this path of injection molding. In parallel with the design of the mold, we explore or we try to find out if laser welding was actually going to work. So we, in our group, some students machine the plates that I pass around. So the single one, as you see, has a black layer. So they machine those plates, and then we send also the transparent layer to the laser welding company so that they can play with different parameters of their machines and see if we can achieve an actually sealed plate. So they send us the samples back, we test them, and they pass the leak test. Then we pressure test some of them, and we had good results. So all of them passed up to a pressure of 60 psi, and even some of them 70 and 80 psi, which is really promising for our application. Okay, so right now, shifting a little bit towards the application of using the heat exchanger in a secondary loop, we want to make a 1.5 ton heat exchanger in our lab. For this heat exchanger, we are going to use the 3D printed pathway just because that's better for quick prototyping. And yeah, and we did some performance comparison with a commercial coil. This is a metallic one as the conventional ones. We use the same capacity and also same cross-sectional area to compare. So here I'm showing the heating and cooling graphs, which we're expecting for a wide range of temperatures to have a higher capacity in our heat exchanger than in the commercial coil. And as you see here, the pressure drop expected is around 50 pascals, which we could not achieve in a two-bank type of heat exchanger. Well, so when we are scaling up the heat exchanger, another of the issues or focus we have to work on is creating the headers that will make the fluid get inside the heat exchanger, right? So that we can enter the fluid and make it exit the heat exchanger. But the problem, or not the problem, but the concern here is that since the channels are really small and we have a lot of plates, we want to make sure that we achieve an even flow distribution. So here for the 1.5 ton heat exchanger, we are going to have 16 stacks of 20 plates as the one that I show you there. But as you see, it has two rows of plates. So that makes a total of 640 plates. As you might expect, since, for example, that one has a lot of pins, every single plate has a lot of pins inside, this is very expensive computationally speaking. So to simplify the simulations, we ran some NSYS fluid simulations, and here it's like a closer view. So we have the complete volume for the header, the vertical header as well as the horizontal headers. But for the plates, we simplify it just having a 10 millimeter section of the plate, which we consider to be a porous media section. So we had to calculate some of the inertial and viscous parameters so that this tiny section could be equivalent to the actual pressure drop that is happening in the whole heat exchanger, so across all the plates. Well, so after we ran the simulation, the yellow line here is showing us the mass flow rate that is expected in every single outlet of these plates. And as you can see, the line is pretty horizontal, so we are hoping to expect an even flow distribution. Here in the right side, I'm showing the mean absolute deviation, and the highest we had was 0.5%, which is pretty good. So we can say that the flow is actually distributed evenly across the heat exchanger. And we run the simulations for a total flow rate of 2 gallons per minute, as well as 5 gallons per minute. And well, finally, the current status of this project is we already assembled the heat exchanger, the 1.5 ton heat exchanger. As you can see, is basically 16 of those stacks that I showed you with the headers as we did in the previous simulation. There are some little adjustments we have to make, because basically like alignments here between the ceiling area and the O-ring. But we are hoping that next month we are going to create the testing loop to test the performance of the heat exchanger for both cooling and heating. And then after we test its performance, we are going to couple the heat exchanger to a air-to-water heat pump here in the WCEC and testing it in the environmental chamber that we have, so that we can test it as a whole system. These just to clarify here, like for example, well, this is going to be the water inlet, then the fluid flows in this direction and exits in this outlet. These white plugs that that you can see here are just the holes for the locating the thermocouples that we want to use, so that in the testing loop we measure the CFM of air, water flow, as well as temperatures at different locations to verify the performance of the heat exchanger. And well, that will be all for my presentation. And if you have any questions, let me know.
So you talked earlier. You were talking about improving the injection molding process, but then you showed like the assembled heat exchangers. So
yes, you mean this one?
yeah. So I thought you were still in the process of building the plates, but then here it looks like it's done. So I'm just trying to.
Yeah. Thank you so much. So maybe I should go to this slide. So for this application, the one that is sponsored by the California Energy Commission, we are going to test the 1.5 ton heat exchanger, which was 3D printed. But for this modular data center, which will have a huge heat exchanger, we are going to be injection molding the plates.
Okay, sorry, I walked in a couple minutes late, so I think I missed that.
Oh.
Oh my goodness. Well, I mean, you can just get a lot of 3D printers.
I won't tell you how much it costs.
Okay. Yeah, like I think right now, if we compare the cost of these 3D printed version compared with the commercial coil, they are about the same price. But of course, when we now shift to injection molding, this is going to be so much cheaper. Yeah.
So can you go back to the board? I think it was the one that was comparing that one.
Yes.
So am I reading that correctly? Reduced data center cooling energy to 5% as opposed to 5%.
As opposed to 40%.
To 40%. Yeah. So right now, So right now the.
Your total energy reduces from 40 to 5.
Yeah. For cooling.
Which is 8.
You're now 90%, right?
Yeah.
That's like, yeah.
90% reduction.
Yeah.
I mean, okay, so that's transformational.
Yeah.
My next question is, this component,
Mm-hmm.
is this component, that, when you think about kind of the housing and this exchange and everything, is the component fitted, like, is that just any air handler would just buy this component and put it in?
Yes.
And so from a translational research perspective, like if we were to think, okay, at the end of the day, we figured this out, does it make sense for this to be licensed by air handler manufacturers, or does it make sense for somebody to start up its own manufacturing manufacturing of these things? What, is that something that's been, you talk about at all with, like,
We have. Do you want to?
So
Oh,
Valentina was part of the, so we have some funds from venture capitalists to commercialize, and we're using that as cost share for the years of the project. The idea is to either, we just got approved for a patent for this design, and so we have the option of either licensing. So we want to get this 1.5 ton test done, then we create our brochure or whatever it is and start circulating to our affiliates to see if they're interested in licensing this for air conditioning applications, or there are other applications in the IEDO project. DO is industrial decarbonization. We're looking at higher temperature polymers. We're looking at waste heat recovery from flue gas streams. So there are a bunch of applications, but we're going to think about strategy. We're not done with it. I'm just waiting for some results.
yeah. Well, I'd be interested in,
Let's talk.
yeah.
But there's a whole bunch of applications for which we can use this.
Right.
That's what's exciting about it.
Yeah, certainly. But it seems like that data center one is remarkable, right? Like,
When we presented this at the kickoff meeting for the Hardware thing, there were people from HPE and others who were very interested.
yeah.
In the data center though, it's the FPHX is one component, but you have got other heat exchanger innovations that are together making it to be
Yeah,
that
that's one part of it. It's a big
Okay.
part of it, but it's just one component. So we're actually going to build out this modular data center in somewhere, probably somewhere here.
That's gonna be a trailer, right? It's gonna be the same size as a regular trailer. Okay.
Yeah.
It's going to be a different configuration. It's going to look different. But yeah.
Okay.
okay, great.
So, you showed a comparison of temperature and energy between a coil and the MPHX.
Yes.
And so, at those mass flow rates on each side, about what is the effectiveness of the MPHX and the coil?
So yeah, I have a slide here. Sorry. Okay, so it's not exactly the same coil, but it's the same type of coil, basically a fin tube cross-flow heat exchanger, metallic one. So that one is the orange one, which is about 0.5 effectiveness, and ours will be like about 0.8 effectiveness. This is a previous generation of the heat exchanger. This was Gen 1, and Gen 2 is the one that I am working on right now, which, I mean, we can expect even higher effectiveness than this, right, Professor Binod? We are hoping to even...
Let's say it's about the same.
Okay, so about 0.8.
And this is the same surface area, but kind of, because you have microchannel, I mean, which creates a lot more area. Is it like the planar area is the same, but you have more microchannels, or I don't even know how you make
So-
that comparison?
Oh, we just think of it as the entire heat exchanger. So you have a fin tube heat exchanger is a cross-counter configuration
Right.
of water flow, and then cross-flow for air, and you have the fin spacing, and all that. So we use the whole heat exchanger design thing, and we compare it against the standard commercial codes available from manufacturers. So we created the EASE code and then compared to the manufacturer code, and it's about the same. And so that's we look at the fin area and all that stuff, right? But there's an efficiency in the fins. You have a temperature change. But imagine that this heat exchanger is basically each of these fins that you have, make it a little thicker, and the entire surface of that fin is at the same temperature, or roughly at a much lower temperature than you would have if you have to rely on conduction. Right? So that's the advantage. And so your surface area, the cold fluid, seeing the warm air, is much larger here than traditional heat exchangers.
Yeah, it just,
Configuration is also
Got it.
yeah.
Got it. So that's the big bump.
Yeah, and just adding up to that, what I meant, like same section, cross-sectional area, I meant this area. So basically the area where air will go in.
Got it.
Yeah.
Got it.
What about the expected comparison in terms of pressure drop across the fan system? Or across the coil that the fan has to provide?
So the pressure drop for our heat exchanger is this one. I don't recall the pressure drop for the other heat exchanger, but we are expecting to have a
Comparable.
It's comparable.
well, yeah. But I think also we are going to be testing the commercial coils, so we will have
Yeah,
like
we'll be testing
in the same conditions the experimental data. Yeah.
Yeah, I mean, that's the only, as long as that's the same or better, then.
Yeah,
And that's,
makes sense.
The thing is that in the traditional heat exchangers, you have a bunch of tubes. So if your airflow is going over it, you have cross flow over tubes, and so there's a wake region, so it's a form drag. Here it's more on the frictional drag because your plates are a little thicker than you have for fins. Right? Fins are what, 300, 400 microns. This is more like closer to a millimeter. So you have a larger, you have basically smaller cross section area for the air to go, but there's no wake region. So it's a balance between those two that sets up the pressure drop differences.
So it,
No, no.
in the diagram, you show it in essentially the evaporator of the air conditioner. Are you thinking of using it in the condenser also?
For the heat pump, it has to reverse. Okay, no, we're not doing it. It's a secondary loop, not evaporator condenser. We can design it for evaporator condenser, but we didn't focus on that. The reason is that when you have phase change happening in one of the fluids, then the configuration doesn't really matter because the constant surface temperature boundary condition. So it's not as good. But if your evaporator condenser have a significant sensible portion, then it will make a difference.
So do you see down the road using it as an evaporator or condenser? So now I understand. This is a secondary loop with water glycol or something
Yeah.
like that, all right? Do you ever see it as being used as an evaporator or condenser in a traditional air conditioner / heat pump?
It's a more challenging application.
Yeah.
But it's a higher.
But I thought you guys were working, or potentially working with a company that you were going to put them in as part of mini split systems?
Yeah, but it's all secondary loop. Yeah.
Okay.
Because they're considering propane, right? They're
that's
considering to 290 and you can't fit 290 into the house. So you need a secondary loop and you need that combination. But we can, to your point, we can design, we just have to change the internal structure so that it withstands the pressure more. But ultimately, when you compare it against a metallic one, I don't know how much benefit you have. There might be other benefits.
But that jump in effectiveness of 0.5 to 0.8 is pretty important.
For single phase, yeah.
Yeah.
So if you have glycol and air,
Yeah.
yes. But if you have refrigerant that's changing phase, it's different.
So the other thing that, as you're mentioning, is pure counterflow, right? So, for example, like refrigerants with high glides,
That would be useful. Yeah.
then that's a big selling point to have match the glide of the refrigerator. So that's where this can become useful then.
Okay. Well, thank you so much.
Thank you.
Hi everyone, my name is Ines. I'm a postdoc here at UC Davis, and I also did my PhD here with Professor Narayanan. And this will be a brief overview of the research I've been working on these last 5 years, which was on additively manufactured molten salt to supercritical carbon dioxide heat exchangers for high pressure, high temperature CSP applications. So there are a bunch of terms here that I'm not sure how familiar the audience is with, so I'll start with defining them. So what additive manufacturing is, why we're using molten salt, and what is SCO2 and CSP. So when we think about using solar energy to power system, there are basically two ways to achieve this. One way is to use photovoltaic panels, so on the left here, on the right side here, where you use the sunlight to basically generate electricity directly. And on the left side is the alternative, where we're basically using heat. So in this case, we focus the sun rays using like some mirrors or reflectors onto a receiver, and we have a fluid that flows to the receiver, picks up the heat, and then run into some processes in order to ultimately generate electricity. So the focus of this research has been this type here. Okay, so on this slide, on the left, you can see a schematic of a solar field. So we have an array of heliostats that focus the sun rays onto a receiver. There is a thermal storage systems where we have 2 tanks of salt. And so once the sunlight is focused onto the receiver, the salt flows into the receiver, picks up the heat, and then is sent towards a hot storage tank, where it is stored up until the time we need to generate electricity. So then the storage system is coupled with the power block and ultimately linked to the electricity grid. And so when we want to generate electricity, the hot fluid is sent towards a heat exchanger. It transfers the heat to another fluid, the main operating fluids in the power block system. And once this fluid picks up the heat, it is sent to a turbine. It will drive the turbine, combine to a generator, and ultimately generate electricity. So we are looking at this component here, the heat exchanger, which is at the intersection between the storage system and the power block. And so on the hot side of the heat, okay, so first, sorry, before we get to the details of the fluid, the main motivation is that for the 3rd generation of CSP system, the DOE is trying to make them more effective by operating at higher temperature. And so if we can increase efficiency, we can make them more cost competitive. And so, yeah, we're trying to increase the receiver temperature up to about 720 Celsius, and the pressure of the fluid will be approximately 200 bar. So on the hot side of the heat exchanger, we use molten salt. And you can see the composition here, sodium chloride, potassium chloride, and magnesium chloride. This fluid is very interesting because it can be used for thermal energy storage, and it can also operate at high temperatures. On the cold side, we have SCO2, which stands for supercritical carbon dioxide. So if you look at this graph here, a fluid is said to be in the supercritical state when it is at a pressure and temperature higher than the critical point. So it's a very interesting fluid because it has an ambiguous set of properties. If you look at this picture here, where we are below the critical point, you can distinguish, the gas phase has a low density. Below here, the liquid phase, higher density, and there's a clear interface between the two. But in the supercritical state, we cannot really distinguish whether the fluid is in the liquid or in the gaseous phase. And as you can see, the density is higher. Well, it's not a completely fair comparison because the pressures are not exactly the same. But the main idea is that supercritical fluids have a density that is closer to that of a liquid while maintaining a low viscosity, which we expect from a gas. So it's really interesting to use this fluid to have energy-dense system and reduce the footprint of power plants and stuff. So additive manufacturing is just it's just like 3D printing, basically. So let's say you want to build this little component here. You start with a stock of metal powder. You will have a laser that will move around, melts the powder. Once you're done with this layer, you add another layer of powder and repeat the process until you build your components. And so heat exchangers for these applications have typically been printed circuits that you can see over there. And so what happened when we fabricate these, we start with a solid plate. We chemically etched the channel. So you can see here it has a set of so red for hot channel, blue for cold channel. We chemically etch these channels. We repeat this process for several plates, and then we stack the plates together. Then we apply pressure and temperature to diffusion bond the core of the heat exchanger, and after that we weld the headers on top of it. The problem with this manufacturing technique is that when we get to higher temperatures, like 600 Celsius, people observe that the heat exchanger typically fail at the location where we have a diffusion bond. So it's not really reliable at high temperature. And also, given the locations of the headers, we have a significant cross-flow region, which means that we have a decrease in effectiveness, like ranging from like 10 to 15%. And so the alternative that we're proposing here is an additively manufactured unit, where we have like more design freedom. So for the architecture of the channels, we can have like more fancier geometries. And it's also monolithic. So everything is built like in a single unit. And basically, once we have like this diffusion bond and the welding, we are introducing some weak points in the design. But if we build everything in a single unit, we don't have to worry about this issue. So here I will start kind of like with a conclusion, what the final heat exchanger that we designed, what it looks like. And you can see it over there. So a heat exchanger, so we have two fluids, right? You have two sides, a hot side and a cold side. On the cold side, we have SCO2 that enters at 500 Celsius, 200 bar. And on the hot side, we have molten salt that enters at 720 C and atmospheric pressure. The two fluids exchange heat, and ultimately, we want to design the heat exchanger such that the outlet temperature of CO2 is about like 7 Celsius and above. We also want to minimize the pressure drop from inlet to outlet. And yeah, you can also notice that unlike the printed heat exchanger version, the headers, just like Valentina showed with the plastic version, the headers are in the flow, across the flow, so that we minimize the region that are in cross flow, and we can have the whole heat exchanger being basically in counterflow. And so you'll notice that, so the schematic here is showing you the cold side where we have like pin fins, and the hot side where you can see that the pins look more like slanted. And so the idea here was to improve the thermal performance on the hot side. So if you look in this table, the little boxed region here, we have the thermal resistance. So RTH stands for thermal resistance. So basically, how difficult it is to transfer heat in that particular section. And so RTH on the cold side is about like 0.07 Kelvin per watt. But if you look at the thermal resistance on the hot side, it's more than 3 times that value. So really the bottleneck to heat transfer is on the hot side. So in order to like improve this aspect, we added these fins that are like basically slanted so that we can increase the surface area, but also promote more mixing so that the fluid has to like turn some more before it exits the unit, and it has like more residence time within the heat exchanger to transfer heat. Yeah, and another interesting aspect of so it's a little bit obstructed, but basically another interesting aspect of this heat exchanger is that we can scale it like horizontally by adding more plates, but also vertically by stacking more units one on top of the other. Okay, so on this slide, I will go over a brief description of what the design methodology looked like. So remember on this slide, the heat exchanger at its most like basic elemental unit is made up of pins. So in the design process, we actually started at this very small scale, looking at the pin itself. So when designing a heat exchanger, of course, we're interested in the thermal performance, how much heat we can transfer, what the pressure drop looks like, but we also want to make sure that this heat exchanger is strong enough to withstand the pressures and temperatures that we'll be applying. So we're interested in looking at what the stress in the unit look like. So the first step has been to run some FEA simulation and see for a given pin diameter, wall thickness, what is the stress state like in the unit. And so based on this simulation, we can identify we can identify some windows for the different geometrical aspects that we can later on refine. So the next step has been to select some correlations. And so these first 2 sections of the design, instead of running completely like CFD simulation and FEA for the whole unit, we've been using a simplified 1D model where we start with a it's a basic like energy balance that we will apply in order to see what the thermal performance look like. So what we're trying to do here is to select a correlation that will best match our experimental results. So what you see over there is a heat sink, and inside of the heat sink, you basically have like the pins that we expect to have in the final heat exchanger. So we run experiments on these, and based on the Nusselt number, friction factor that we're observing, we compare these results to the experiment to select a correlation in the literature that will best represent the thermal behavior of our unit. After selecting the correlation, we conducted an optimization / parametric study where we go back to the set of like pin diameter, wall thickness, channel width, and all that we had to come up with a best case scenario that we'll be using for the heat exchanger. And after selecting this best case scenario, we actually run some CFD and FEA simulation to look at, so in the CFD, we want to look at the thermal performance, but also obtain the temperature distribution within the heat exchanger so that we can assess the thermal stresses. Thermal stresses that will be added to the mechanical load, so the pressures that we have in the unit, to have a combined thermal-mechanical stress of the heat exchanger. Once we have this thermal-mechanical stress, we want to check whether the design is within our margin. If it's not the case, we need to go back and look at a different set of parameters, run against CFD and FEA. But if it is validated, we can now look at the creep and fatigue performance. So creep and fatigue are modes through which heat exchanger can fail. And so we just want to make sure that with respect to those, the heat exchanger is relatively safe. And once this is validated, we can actually print a full-scale heat exchanger that we'll be experimentally testing and ultimately compare the performance of this heat exchanger to the model that we had somewhere in the middle over there. So for the sake of time, I will not go over every single detail, but basically here you can see the printed, like some printed prototypes. They were printed by Carnegie Mellon University. So as a disclaimer on this project, all the design and experimental testing were done by UC Davis, but all the printing were done by our colleagues at Carnegie Mellon University. So these units were printed out of Haynes 282, which is a nickel superalloy. And so after printing, we assembled them. And as you can see here, on this one, you have like a relatively large unit with about 26 plates. But in the final version that we tested, we had 4 stacks of 6 plates. So the idea behind this was to demonstrate the vertical scalability that we mentioned and show that experimentally it's able, it's sustainable. And so on the cold side of the stack, we have supercritical CO2. But then on the hot side, since there's no chloride salt loop that we could bring the heat exchanger to test. So instead of salt, we've been using hot air as a surrogate fluid. And yeah, we ran the experiment and compared the thermal performance to the model that we had. There was a very good agreement. And so just to give you some numbers, for the exit temperatures of on the cold and the hot side, we had about a 0.8 or 1.5% difference between the model and the experiment. And for the heat transfer rate, it was less than 1%. So this validated the model, and that was basically it. And this last slide here is to emphasize the fact that we can use this heat exchanger for much larger application. So when we think about power generation, people think in terms of megawatt scales. And our little heat exchanger is about 20 kilowatts when we use molten salt and CO2. So by stacking a few of those units, we can achieve a 1 megawatt configuration. So the work on this project has been sponsored by the funding of the CITO office, and we also received funding from ARPA-E. The simulations were run, a lot of the simulation were run using the high-performance computing system of NREL. And yeah, these are my sources, and thank you. Yes.
So, is this supercritical CO2, which essentially runs through the turbines, is that also used in coal power plants in the newest ones, or is this only in these concentrating solar power plants?
To be fair, I am not sure, but I'll imagine that supercritical CO2 is not the new concept. It's been existing since like I think like late 60s, but I don't know if the coal plants have been using it as well. I'm assuming they use steam mostly.
It's a cross-cutting program. They call it cross-cutting program in DOE. So the fossil energy, nuclear, solar, and geothermal, they're all looking at this. So they're putting in money to develop the power block for the CO2.
So supercritical CO2 is a fluid that can be used in
Yes,
multiple.
and in fossil there are two options to use it. The easiest one is the closed loop. The CO2 is just within the loop. The other one they're thinking about is for actual adding it into the combustion process. Like, so let's say you have oxy combustion. You have really high temperatures. You have CO2 as an end product, and you sequester that. It's already compressed. So those are two different options they're looking at. Second one is further out there.
Interesting.
But nuclear and probably the one that's closest to application is, I would say, nuclear.
And I'm just, showing my naivety, but it's interesting to me that additive manufacturing is to the place where you're able to additively manufacture something which is stronger than subtractive. It's something that's just steel and etched out.
Yeah.
That's amazing.
In the 5 years of this project, at the start, in 2018 when we started this project, this was the first project that DOE funded for additive and solar office, and they were very skeptical about it. In the first budget review, we got slammed because we were not getting the features that we thought we would get. But then we just closed out this project in January. They were fascinated by what we had accomplished in terms of we can build heat exchangers not to the megawatt scale, but we show a path towards what you can do. And there's another cost component of it. The Park Vaishnav at Michigan led a cost, like process-based cost model, and we can show that we can hit their targets at the scale that they want. It's expensive, but if you can build it out to the scale, then it's possible.
So, and then to step back even further, concentrating solar power was hot and then cold and hot and cold, and I think it's cold now.
It's probably cold now.
Yeah, because the PV just keeps coming.
Yeah. There's no way you can compete with it. One of the aspects of the project, not this one, but the receiver project, is looking at process heat. Is that a possible application? So we're working with a company called Sun Vapor. They're in California. They have the only two process heat plants in the US. And they're doing techno-economic analysis for seeing if process heat can be an application for solar thermal. And it's without incentives, it's really hard. You can't compete with natural gas. So,
Yeah, but it seems to me that CSP, with this thermal storage, could eventually come back when when we're really trying to push zero, right?
Yeah, exactly.
Because we can run these things at night, and PV,
Exactly,
PV
yeah.
it's batteries and
Yeah.
stuff, but you might be able to just store enough thermal energy during the day to run it through the night.
I mean, at this point, you're right. When you have a push towards zero, then you have to look at all these options.
Right.
But right now, there's no way that even electrification or this technology is going to work compared to natural gas. I mean, some people are looking at a case study for drying, high temperature drying in Texas. Okay. They're paying $0.50 per million BTU.
Oh yeah, but that's not your target, right? You know,
per term, right?
Yeah.
And if you put all this together in the most idealistic scenario, you're at $2.
Yeah, exactly, but that's not the target, I think, is against natural gas. It's a renewable energy.
This is exactly
target.
what we are pitching to DOE, and DOE is nodding their head and saying, yes, we are not comparing against natural gas, we need to compare against other renewable technologies and see if this makes sense versus
Yeah.
electrification. And that's exactly what we're
Absolutely,
pitching.
absolutely.
That's where we're heading right now. We'll have an answer in a few months.
I had a question. So on this, the molten salt part, so that seemed to be the with the one with the higher resistance, right? Higher thermal resistance. Were you able to do any kind of optimization on that side? Like you showed some pins, right, to increase the right there.
Yeah.
Was there any optimization or analysis done on this side?
Yes, not in terms of strong like optimization, but looking at a few cases, because the problem when you keep adding these fins, you increase the pressure drop, and there's even cases, especially with additive manufacturing, you cannot really guarantee that your final product is going to be exactly the way you design it. So you might have like some more clogging. So we try to design these fins so that we decrease the thermal resistance, but still don't end up with a prohibitive pressure drop.
How is it being? Is there a pump that pumps this molten salt?
Since we haven't had the loop to interact with, I don't know.
There is no functioning chloride salt loop in the US. Let's put it that way. So in the US, there is no functioning chloride salt loop for testing. Oak Ridge was given money, they put a loop together, but they ran out of money to test. And then they changed pathways. So we work with NREL. NREL has corrosion test facilities, but these are static corrosion tests. So we print out additively manufactured samples, and they have a test cell with the same salt, and then dip it in there, see what the corrosion rate is. So there are different aspects to this that we have.
So that's interesting. So these pressures would be a positive displacement pump, right? And the question is really corrosiveness.
Oh, it's nothing to do with
the pressures.
Not even the pressures are not very high,
Right.
but the corrosive nature of the fluid is what's the problem.
Yeah. And the seals on the.
Yeah. I actually visited Mark Anderson's lab at Wisconsin, and he's working with some pump companies that kind of modified the seals on their nitrate salt pumps and tried to do chloride salt, and he was saying it was not good. It was leaking like crazy, and there's a lot of corrosion issues. It corrodes through the seals.
That is like the biggest challenge, then, to move the fluid,
Yeah.
move the salt. Is there a reason behind choosing this chloride salt versus some other?
Chloride salts, nitrate salts, that's what's used in the first generation of solar thermal with storage. Back to solar 2 in the 90s, that is basically sodium and potassium nitrate mixture. It degrades or decomposes at around 580, 595 degrees Celsius. And so if you want to go any higher, if you want to go to 720 for CO2, you need to go even higher for salt. So this composition of the ternary mixture of chloride salts is one option, but it's highly corrosive. Australians are actually looking at sodium, and sodium is probably, sodium is a really good heat transfer fluid, and it makes sense to use it. It's just they have chosen the sodium path, and I think DOE also worked with chloride salt, sodium with the Australians, and they ultimately agreed that sodium is probably, if you're going with a liquid for this application, it should be sodium. But DOE has not been funding projects on sodium because Australia is funding it, and there are huge implications of safety with sodium.
Liquid sodium?
Yeah, sodium. If you have a leak of sodium, you have a fire.
Yeah, that's like pure sodium.
Yeah, sodium, metal.
Well, thank you.
Thank you.
Thank you.